I love that box.
Okay, so the decomposition of hydrogen peroxide is what we're discussing here, right?
Yeah, maybe just say.
All right, so if you look at that and say, hey, what parts would this break into? The obvious answer to most people would be hydrogen and oxygen, but that would not be correct. So peroxide is a very common substance that does a kind of strange thing. It breaks down into water and oxygen, which is not something you would probably figure out just by looking at it on paper. So the reason they put it in that brown bottle is if they did not, they packaged it in a clear container. By the time it was shipped to the store and was taken to your house, all that, all you would have left is just a bottle of water with a bunch of oxygen gas. So it's put in a brown bottle so that chemical reaction doesn't happen.
So when it's exposed to light, that's when that
That'll happen.
Okay.
And other ways, but light.
Why does it break down exactly to oxygen and water instead
God
of?
said so.
Okay, God said so.
So like if I go home and pour the hydrogen peroxide in a like clear plastic cup and take it outside, it'll turn it to like pure water. Like pure water. Like drink it. Like I could drink it.
You'd have to know, I don't know how long it would take. You'd have to have a way to know fully decomposed.
That's really I'm gonna do that. But I'm gonna look into it. I'm gonna do that. I'm gonna let you out.
All right.
I know we're.
Here we go. All right, combustion, next. Combustion. Something reacting with diatomic oxygen. Here comes that diatomic word again, right? We have to be able to remember our diatomic molecules, okay? So anything that reacts with O2 is burning or combusting, whichever word you want to use. All right, and the products are going to be the oxide compound of whatever it is that you burn. Okay? So whatever, anything it is, doesn't matter what, plus O2 yields some type of oxide. A couple of examples. Magnesium is a metal, right? Left side of the periodic table. Everybody got their periodic table in front of them, by the way? Just a reminder. It makes more sense if you use the periodic table. If you react magnesium with oxygen, we'll do this demonstration in a few days. Okay. You react magnesium with oxygen, you're going to get magnesium oxide. That's the oxide of magnesium.
No, not.
All right, the second example is a very important one. What is that substance right there? Somebody said it. Methane. That's methane.
Good job, Julia.
Very good. All right, so methane. Methane is a hydrocarbon. The simplest hydrocarbon contains hydrogen and carbon and nothing else. If you combust that, write this one down. This is a little fun fact we have to know. This is definitely the test. If you combust a hydrocarbon, the products are CO2 and water. Every time. Combustion of a hydrocarbon produces CO2 and water.
Wait, what? If you combust it, what?
Hydrocarbon. Something that contains just carbon and hydrogen. All right, side note, this will definitely be on the test too. If you add oxygen to the compound, so if you have a compound that has just carbon, hydrogen, and oxygen, the products will also be CO2 and water.
What's the last one?
If you have carbon, hydrogen, and oxygen, then the products are also CO2 and water.
Oh, that's if they combust.
Oxygen. If the compound contains carbon, hydrogen, and oxygen, and you burn it, the product is CO2 and water. Okay, you got that? Reaction type number 4, single displacement. So we described displacement yesterday by saying it was removing something from its spot and taking its place. So we can recognize a single displacement because the reactants are going to be one element and one compound, not two elements, not two compounds, but one element and one compound. Okay, that compound is going to be, in most cases, okay, in cases that we'll see at least, that compound is either going to be ionic or it's going to be an acid. Okay, the element, of course, has to be either a metal or a non-metal. Depending on what combination we have there, that's going to tell us what's going to displace what. And there are 3 possibilities here. The element could be a metal. If the compound is ionic, then the metal will displace the metal from the ionic compound. If we remember, hopefully, that ionic compounds, we identify them because they contain a metal, right? So they got a metal and a non-metal, what we also call the cation and the anion. The metal will displace the metal from the ionic compound. If the pure element is a non-metal, then it will displace the non-metal from the compound. If it's a metal and an acid, then the metal displaces hydrogen from an acid. We may have said this before, but jot this down. Okay. Hydrogen wishes it was a metal. It's sort of like a pretend metal. It's not a metallic substance, but it likes to act like one. So much so that it's in the first group with a bunch of other metals. But it's not a metal. But it sure does act like one sometimes.
So it can be displaced by another.
Yes, it can be displaced by another metal. All right, so that's the 3 possibilities for single displacement. Yes.
Okay, and then so if hydrogen can get displaced by metal, can it also get displaced by non-metal, or will it just be displaced by metal?
Not normally.
Not normally, but it can.
Maybe. I have to think about that. I have to think about an example, but I hate to say no because there's so many exceptions in chemistry. To say never, but I'm sure there's some case. All right. Example. Zinc is a what? Metal or non-metal?
Metal.
Metal. What is HCl?
2 non-metals.
Okay, so what?
Oh, that's chlor.
It's an acid, right?
It's an acid. Very good. It's an acid. Okay.
Dang.
All right. So the zinc is going to displace the hydrogen from the acid. Okay. So the hydrogen kind of acts like a metal. The result of all that displacement is now we have, instead of hydrogen chloride, we have zinc chloride. Zinc took hydrogen's place, bonding to the chloride. That leaves hydrogen out here by itself. Hydrogen is now what we call a free element. Okay? So, metal can displace metal, non-metal can displace non-metal, or metal can displace hydrogen. 3 possibilities that we'll see. All right, number next, double displacement. 2 compounds react to produce 2 new compounds. Okay? If single displacement is like somebody cutting in on a dance, double displacement is like a square dance or something where the partners just switch up with each other. Okay? 3 types here also, and these 3 types are identified by looking at the products instead of the reactants. Single displacement, we identify the 3 types by looking at the reactants. Double displacement will identify the 3 types by looking at the products. Products are going to have to be either a solid, a liquid, or a gas. You've got to produce at least one of those. Could be more than, but at least one of those 3 phases. In other words, if both products turn out to be aqueous, then you don't have a chemical reaction. At least you certainly don't have a double displacement. All right. When we're doing double displacements, we've got to be able to identify the cations and the anions. And then we got to remember that we always order things in that order, cation, anion. Okay? So if you look right here, what's sodium? Cation or an anion? That's a cation. What's chloride? That's an anion, right? Silver is a cation. And what's the anion right here? What is that stuff? We all remember our polyatomic ions, right? Huh? Nitrate. Yep, very good. That's nitrate. Everybody remembers their polyatomic ion. Yeah. Okay. All right. So we've got sodium, we'll call it cation number 1. Chloride, we'll call it anion number 1. Silver is cation number 2, and nitrate's anion number 2. So it's going to switch up. So this is cation number 2 bonded to anion number 1. They just switched. And the second product is cation number 1 bonded to anion number 2. Everybody just switched partners, but the products are still written in the order of cation, anion. Okay. Last one. Anhydride reaction. Substance reacting with water. Okay. 3 examples that we'll run into. There are others. Okay. If you put a metal in water and it reacts, okay, the result is going to be that metal hydroxide compound and hydrogen gas. So, for example, if we just took sodium and dropped it in water, the products would be sodium hydroxide, a compound of sodium hydroxide, and hydrogen gas. Second possibility, if you took a metal oxide like sodium oxide, put it in water, you're going to get sodium hydroxide. Write this down for me, little fact we need to know. Basically what the second line says. We're just going to kind of put it in words here. Metal oxides in water make bases. We need to know that fact. Metal oxides and water make bases. Base being opposite of an acid. Metal oxide and water make bases. Example number 3 is sort of an opposite here. Non-metal oxides and water make acids. So metal oxide and water makes a base, and a non-metal oxide and water would make an acid. Specifically, an oxyacid. Do we remember that term from a while back? Oxyacid contains what? Oxygen. Okay? All right, so there's the 6 definitions. Some examples. Now, we'll get to the good part here. Yes. We are going to learn to write balanced chemical equations for situations like these. Okay, so these are your practice problems that are linked to the slideshow. These steps to writing a balanced ionic equation are also linked there. Okay, take about 2 minutes. Read through those the first 6 steps right there. You can read all 9 if you want to. First 6. We won't do it today. Take a couple minutes to read through that. So you didn't read through it last night. All right. So what we're going to learn to do between now and January the 30th is to take statements like we have on the right, like number 1 right here. Okay. That statement, ammonia is synthesized from nitrogen and hydrogen. Okay. Just a brief description of something that took place in a lab or in nature or wherever. Okay. And we're going to take that statement and we're going to construct a balanced chemical equation that represents that. And we're going to do it by following these steps right here on the left-hand side. We're going to follow them in order and separate from each other. If you try to mix them, blend them, get them out of order, whatever, you're going to mess it up. Okay. Step number 1. We're going to write the formulas for the reactants. And the reactant names are given. So let's read our statement again. Ammonia is synthesized from nitrogen and hydrogen. Okay. So what are the reactants?
Nitrogen and hydrogen.
Nitrogen and hydrogen. Everybody follow that, right? Because the reactants are what you get products from. Okay. So take a minute and come up with a formula for nitrogen and hydrogen. And then somebody put them on the board, like we're going to write a balanced equation. In other words, separated by plus sign and write it kind of big and leave some space and all that. I'm going to add some stuff to it. I need a volunteer at the board.
Mr. Cato, how would you exactly write out those?
Oh, wait a minute. Time out.
What's RXN?
Just the reactants. RXN means reactions.
Okay, just react.
We wouldn't use an equal sign. What do we use?
Arrow.
Arrow. Okay, and that's, well, that'd be big enough now. But it's a little crowded. You're going to spread it out, rewrite it, kind of spread it around a little bit. We're going to have to put some stuff in between in just a minute. What time we get out of here?
24.
Very good. Just for the fun of it, because it's going to drive me nuts. It does. It's not wrong. Put nitrogen plus hydrogen. It's just because it's going to drive me crazy.
Why is that?
Because you'll see. Just flip it around.
Wait, isn't it 50 goes nitrogen and hydrogen first in the problem? Yes.
It's going to look so much better when we get finished. All right, leave it right there. Okay, next. So that's step number 1. All All right, and only step number one. So say we already had a situation there, we tried to get ahead of ourselves, right? Now, step number one, just do step number one, right? The formulas for the reactants, okay? So you got to read the statement, identify what the reactants are, and you got to sort of step to the side, come up with the formulas. These are pretty easy, these two examples, as long as you remember that they are diatomic, okay? So you don't leave off those little twos. Step number two, determine the type of reaction. That should be really easy in this class because it's probably going, well, the question is going to tell you the type of reaction. You get to the AP class, it doesn't do that, okay? So if this were AP, here's what we would be doing right now, number two. We would look at nitrogen and hydrogen. We would say, well, what could that possibly do? And we're going to do a process of elimination. It's two elements, so it can't be a decomposition. Neither of them are oxygen, so it cannot be a combustion. There's no compound up there, so it's not single displacement or double displacement. And there's no water, so it's not anhydride. So it has to be a synthesis, right? So that's why we got to learn those definitions, okay? Because when you get to the real part of this next year, you've got to be able to put all that together and figure out what that's going to do.
I thought it synthesis because it was synthesized.
Yes, next year
But it
we'll
won't
say
say
that.
that. Okay.
Yes,
I
next
see
year
what
we'll
you're
say
saying.
that. There you go. With this class, it's going to tell you what type of reaction is going to take place. You still got to know the definitions because that's got to help. That should ring a bell now. Synthesis means that this is going to make one product, right?
A plus B.
Yeah. In this case, nitrogen and hydrogen is going to make one product, okay? So, moving to step number three, determine the name of that product. If this were AP class, you would then be figuring out what that product is. And you would say, well, nitrogen and hydrogen, if they synthesize together, it's going to have to be NH3 because of the octet rule and the structure and all that we learned about, right? You have to put all that together and figure out what those two things would combine to make, okay? And there might be multiple possibilities. When I ask these questions at the exam, there's often multiple right answers, all right? But this class, it's going to tell you. You just got to be able to read and figure out which one's which. So which one is the product? Ammonia, okay? So again, AP, we have to figure that out. In AP class, this statement would say nitrogen and hydrogen are mixed. That's all it would say. Okay, you would leave out the product name, it would leave out the type of reaction. All right, so now we go to step 4 and we write the formula for the product. So somebody go to the board and put the product up there, its formula, hopefully correct. Don't write it too close to the arrow because you got to leave room for a number, possibly. Maybe not. Quickly, somebody, we got 6 minutes. We got to go. So we should remember the formula for ammonia because it was on that quiz we took. Remember that quiz? We had methane, ammonia, carbon dioxide, water, and all of the information about it, right? We took that quiz, everybody memorized it, like everybody made 100 on it, right?
Mm-hmm.
Remember that one?
Yeah.
Good. We should know what ammonia is. All right, correct. Step number 5, balance the reaction. Here we go. Ball conservation of mass says that what we start with is what we got to end with, okay? Right here, I'm starting with 2 nitrogens and ending with 1 nitrogen. That's a violation of the law of conservation of mass, right? Starting with 2 hydrogens, ending with 3. That's a violation of the law of conservation of mass. So something's not right here, okay? We got to fix that. We got to make them the same on both sides. So if there's 2 nitrogens over here, there's got to be 2 over here. And here's what you cannot do, and write this down because people will do this, no matter how many times I say it, people will do it, okay? To balance the reaction, you cannot change the subscripts. You cannot change the subscripts. If you do that, you're throwing the whole thing off. The whole thing's going to be wrong. We determine the formulas for the reactants in step number 1, right? They don't change. We're doing these steps independent of each other. right? Okay. We determined the subscripts for the products in step number 4, so that's going to stay that way. The only thing we can do here to balance it is add coefficients. So if there's 2 nitrogens over here and we need 2 over here, we've got to put a 2 right there. That makes 2 nitrogens. Now how many hydrogens do I have on the right? 6, because it works like the distributive property, right? 2 times 3 is 6. So if I want this to be 6, I change that to a 6.
Mm-hmm.
And what do I do? Put a 3 in front of it. There we go. Good. That's balanced. Oh, I got 3 minutes. All right, this is going to go quick. Don't leave when the bell rings. I need to finish what I'm saying here. Here comes your homework for tonight, too. Determine the phases, step number 6, okay? By the way, step 7, 8, 9 don't apply until we get water in the mix, okay? Step number 6 is to determine the phases. There's no water here, so we'll be finished after step number 6. Tonight, your homework is to learn these 5 facts, okay? Number 1, ionic compounds are solids if no water is present. If water is present, refer to the solubility rules to determine if they are aqueous or solid. We will get around to those on Monday, okay, those solubility rules. Number 2, metals are solids except mercury is a liquid. Number 3, nonmetals. This is where it gets a little, could be a little of anything. Nonmetals are solids except hydrogen, nitrogen, oxygen, fluorine, and chlorine are gases. Well, there was our hydrogen and our nitrogen, right? So what are hydrogen and nitrogen? They are what? Gases, okay? Bromine's a liquid, iodine's a solid, noble gases are gases. So here's what we do, okay? To designate the phase, in a parentheses, subscripted, printed letter right there, a G, lowercase g, okay? And right here, put a lowercase g in parentheses, subscripted. Okay, and that designates the phase of those 2 reactors. All right, real quick. Number 4, covalent compounds can be solids, liquids, or gases. What is ammonia? It's a covalent compound, right? So number 4 is going to apply to ammonia. It could be a solid, liquid, or a gas, depending on size and polarity. We learned about that right before Christmas. Most problems will tell you the phase of a covalent compound. You should know some of the common gases, though, such as CO2, CO, ammonia, methane, nitrogen oxide, and sulfur oxide. You should know that those are going to be gases. And you should know that water is a liquid and ethanol is a liquid. So ammonia is a gas. Okay. Number 5, any substance that is water soluble is aqueous. These would include the acids, any ionic compound that follows the solubility rules, plus any other polar covalent molecule. And those solubility rules we will discuss next week. Okay, so all 3 of those are in the gas phase. That's what we call an all gas phase reaction. Everybody's a gas. All right, and that got us through step number 6. 7, 8, 9 don't apply because there's no water. We'll pick back up with this on Tuesday. Please study over these phase designations.